Welcome back to another Femap tutorial, everyone. Let's take a look at setting up a sinusoidal acceleration function and applying it to this plate. I set up this plate already. If you don't know how to do it, go check out some of our earlier videos. This is a simple geometry with lines, rectangle. One side is 10, the other one's 20. I set up some material properties. You can go in the edit and let's take a look. I only entered E, the new, and some density, and also properties. My plate, I set up a plate. My plate doesn't let me to change the property anymore, but you can tell it's a plate element type right here, and I added some kind of thickness. Okay, that should be all. And also I meshed it. I went to mesh control, size along the curve. I added 10 on these sides and 20 on these sides, and then I actually meshed it, and there you have it. Okay, so next step would be to let's go ahead and set up a function that represents this guy right here. So for that you can go either right here to functions or model functions, same thing. And here, let's see, I'm gonna call it acceleration function. Right? Dimensionless, we're gonna change to something versus time. Right? For us it's gonna be acceleration versus time. So on the x-axis, time, and here we are setting up our factor, which will be our acceleration. Here we don't select what's on this axis. We're gonna select that later on. Right now we're gonna code in the function of this function that we're gonna be working with, and then later we'll assign its meaning, which when we go to loads, we're gonna assign is it a force, a load, or acceleration, velocity, what is it? Okay, so right now we're setting up a function based on later what we're gonna tell the loads what is it. So this is gonna be an equation right over here. On variable on the x, we can leave it x, and let's see, we're gonna go from 0 to 1 on the x direction, and our function is gonna be a sinusoid function, right? So sine, and make sure you enter your degrees in degrees, not radians. Okay, don't put here 2 pi, put 360, and times our variable is gonna be time, which usually we mark as time, right? But here it's on the x-axis, so the software needs to understand x, and since we are referring to one of our global axes, make sure you don't forget that you need to put an exclamation point and then on the x. Okay, so that otherwise the software is going to get confused. So 360 times exclamation point x. Okay, so if we go ahead and add it, let's see what happened. Oh, we didn't put nothing here, so 0 to 1. Oh yeah, okay, we put here 1. Let's discretize it a bit more. Say 1, 0.1. How many times do we want it to break this time interval up? Okay, 0, 0, 0, and let's go and re-add this one and see it made a nice table of all the numbers. And we can also kind of see the sinusoidal function right here, but it is kind of choppy. I don't like it. I want it to be a bit more finer defined, so that's where this comes in. See, we can put 0.1 instead there. Let me reset it first, get rid of that. 0.01. Let's go back here, 0 to 1, and add it again, and look at that, how much smoother it shows it. So this is a quite good feature, because it helps you check and make sure that, hey, if you messed up, you can at least visually right away check it. Okay, so now we are here at the end of our function at time 1, right? So if we would model whatever we doing past this 1, then the software will extrapolate our function based on these last values that it sees right here. So if I would model my analysis past the 1 second, it would continue this function like this. And I don't want that. I want it as, we came back to 0, and I want it to make sure that it continues as 0. Therefore, from this point, we need to define another point further down the line from where, if it extrapolates, it understands that it's gonna continue further on as 0. So, see, it automatically jumps to the last point where we were, so that it was 1, and let's say I'm gonna go all the way to 2 or some point further down in time, and I want it to be a constant of 0. Okay, so we don't need to have, you can leave this here, but it's going to be useless additions in the table, so you can just put 1 x and add it, and there you go. Now see, it just added another entry into our table, and it understands from now on that bam, we arrive to 0 and we stay at 0. So if I run my analysis to up to 10 seconds, it will understand that even though we passed this function after time 2, it will continue the straight 0 line. Okay, that's all. So we done with this guy. Yep, close it out, cancel. Now let's go ahead and actually set up our load, which will be an acceleration type of load, right? So we don't have specific designations like that, so it's going to be under the load on a curve, because I'm going to add it to one of these edges, probably this one. So let's see, load set, let's see, f external. Okay, I'm gonna pick this one. Okay, I'm gonna apply it to that whole edge, and this is where we're gonna define what that function will do. Okay, so title acceleration, yeah, there you go, that's good enough. And see, I could use the same thing for a force function. If I leave it a force and go here and pick acceleration function, this is what we defined over here, right? This is what we just defined with the sine function. Here we select it and tell the software that, hey, pick that one. And what am I going to use it for? I can use it as a force, and let's say apply it in the x direction. I can use it as a torque, displacement, velocity, but for us, I'm going to use it as an acceleration. Okay, let's see, I want to move it like shake it in the z direction, right? So I'm gonna make sure I specify that for him. So z1. Okay, so this is like a multiplier, so use this function in the z-axis, okay, with a multiplier of 1. That means use it as is. If I want it 10 times stronger, then you would put a 10 there. Okay, so that's what that means for us, and I believe, yep, that's it. Okay, and now you see it set up the load as we defined it right here. Now if you guys remember, in our previous videos we said that when you set up one of these kinds of cancel that out, special kind of loads, you need to make sure that after you applied this load, initial displacement, initial velocity, acceleration, or this one like a forced kind of what is it, forced function for the acceleration, we need to go back after we set up the load and also constrain the direction of motion in which this load acts. Okay, if we don't, the software will throw an error. We will not understand what we want. I know it can be a bit counterintuitive, but that's how the software requires it. But you know what? Just for the sake of the video, let's make a mistake. We're not gonna constrain the direction. Let's run the analysis as is. See what happens. Okay. So analysis new. I'm gonna call it 1. Here we're gonna. This is gonna be a transient dynamic time history. This, if you interested in what kind of theory is this running, this is running a Newmark's method. Okay, so if you wanted that, okay, we need to go dynamics, not defined. Make sure you define this one. Let's see, number of time steps. We want it. Let's do 1,000 time per step. Let's do 0.001 and output the calculation data that you made in every single step. We could make it every 10 steps or whatever you want, how often you want it. For me, it's not that big of a calculation. Each time step is just fine. Okay, we can also go down here and output requests. Click on one of these, double click it, and this window will appear, and check what kind of results will it give you. Sometimes maybe you want also velocity. You can put it, click it. Yeah, maybe I want stress as well, and click it, and okay. And let's go ahead and analyze. Let's see. And right away it found our error, right? We knew it's gonna come. So there you go, fatal errors. Right, it's telling you here not much. Show detail, there you go. Well, not much, but a better way to check what's going on is go to the working directory where you save the file, and there's a bunch of files that it's working with, and go to the FO6 file. Double click it, it's gonna open a text file. There you go. And here's all kind of stuff that Femap is writing for us, and press Ctrl F and find fatal. Write in fatal right here, click on it, and it will go down and find where it's trying to describe you what is going on. This transient response analysis has no excitation specified for it. Applied loads, enforced motion, initial condition, and nonlinear forces are all null. The result will therefore be a zero solution. Okay, right? Interesting. Did you guys understand anything from that? So the main sentence is kind of this one, that there's no excitation specified for the situation, so he cannot run it. Well, actually we did specify an excitation, we just forgot to constrain the direction along which it needs to be acting. So we can go ahead, and all we need to do, click the right on constraint, right click new, or go to model constraint, and on the curve we're gonna constrain it. Let's call it boundary conditions. Okay, pick it. Whoa, did I pick the right one? Yeah, okay. All right, and this one called edge, and we must constrain the z, because that's along which direction we decided to set up our function to control the motion, right? So that one needs to be made sure that it is constrained, but we also can make sure that we constrain all the other directions. I don't want it to start slipping and sliding left, right, and rotating this whole thing, so we can also zero these ones out just for extra security. And okay, that's it. Cancel, and we can go ahead and run our analysis again, and let's see what kind of answer are we gonna receive now. There you go. So model analysis, I'm gonna do a new one, call this 2. We transient dynamic. Okay, we need to go back and set these one not defined to 1000, 0.01. 1. Okay, and I'm gonna do the same here like we did there. Velocity, stress, okay, and done. And let's go ahead and analyze. And let's see, did we mess up something else, or are we gonna get a successful completion to our analysis? Come on, you can do it. We're waiting for the solver. There you go. It's running our, going through the time steps right now. See the 1000 time steps that we requested. Come on, come on, put you back into it. Let's go. Almost there, almost there. And there you go. We do not have any fatal error messages. Our simulation completed. Awesome. Now if you wanted to rerun the previous analysis, right, this one, then make sure you remember that let's see, under boundary condition right here. So if you would just if you set up this constraint, right, you cannot just come back to it and then hit analyze again. You will get the exact same error because it does not update stuff. So like go to boundary conditions and double click on this one, and it opens up all the everything that it contains here. And see, it's constraints. None. It didn't. We added a constraint, but it did not update it. So if you want to rerun this, make sure you go into the details and update it. BC. That's what we called our boundary condition, right? We have boundary condition. Make sure you tell him that, hey, constraints right there, BC. The loads is the function that we selected. That one's fine, right? All good. So okay, and now you could run and well, actually let me run this one. There you go. Now you could run it and it'll go through it and it'll give you the same answer like the number 2 that we just did. Okay, there you go. It's complete, no errors. There you go. Now let's visualize. Let's see what we got here. And all results, let's say, we can even right click and where is it? No descend output vector, no contour envelope. Okay, there you go. Nice, nice. But I believe there should be one here too. Oh, there you go. Deform. It shows you how much it deformed. Let's see. At 0, let's do this one. Deform. There you go. See, let's pick this one. Deform. Nice. I can kind of see how everything propagates one by one. We'll go further down the line. Let me see this one. Deform. Yeah, nice. So these are basically the pieces that you see wiggling around over here, right? What if I let me go to view, select, deform, contour, deformation. I want to see the von Mises stress. So plate, where are you? Von Mises right here. Plate top von Mises stress. Let me see how that one looks like. There you go. Look at that. You can tell how things are getting stressed. Let me see that. Nice. And then you can pause it at a certain point and have that deformation and analyze it. Oh, what kind of stresses do I have at time 0.2? Or go down to, I don't know, 0.9, right? Well, let me see the deformation. How do we stand? Where are the stresses? See, not at the tip, and they are further down the line right now, the highest stresses. All right, so there you go. Well, thank you everyone for tuning in for another Femap tutorial. Make sure you like and subscribe and have a great day.